What if I told you that the invisible forces that power every single digital interaction in your life, from that instant message you just sent to a global financial transaction that just occurred, are undergoing a silent revolution right now?
Mm.
This revolution isn't just reshaping how we connect, it's fundamentally changing how businesses operate. And, critically, how you can position yourself for a future-proof career.
Absolutely.
From the cloud to your coffee maker, everything is connected. And it all starts with data communications. Welcome to The Deep Dive. Today, we're plunging headfirst into the fascinating, ever-evolving world of network architecture.
It really is fascinating.
This isn't just the backbone of all data communications. It's like the nervous system of our digital world. We'll be unpacking the core concepts behind how modern networks are built, secured, and managed, drawing insights from a rich stack of sources.
Yeah, quite a few good ones today.
Including a deep exploration of network architecture fundamentals, the magic of virtualization, cutting-edge cloud strategies, and the transformative power of automation. We're pulling wisdom from industry leaders like IBM and Juniper, academic texts like the CompTIA network plus guided networks, and research from CSPi Technology Solutions and CloudDefense.ai.
And this deep dive isn't just about collecting facts, right? It's about giving you the critical lens to understand and influence the digital landscape around you. Whether you're studying or working in business, IT, MIS, or CIS, perhaps even here at Tarleton State University's Dr. Sam Pack College of Business, these insights are, well, they're truly crucial.
Definitely.
We're going beyond the jargon to show you how to, identify the right networking components, strategically design robust networks, fortify them with cutting-edge security, deftly troubleshoot complex issues, and ultimately craft professional network proposals that solve real-world business problems. A fluent grasp of these technologies isn't just essential for navigating our digital-first world. It's your strategic advantage for career growth and industry certifications. It really is.
Before we unpack this, if you're finding value in gaining these insider tips and understanding how to position yourself for a bright future, please do us a favor. Like this deep dive, subscribe to the deep dive, and maybe share it with someone else who's curious about the future of tech.
Yeah, that'd be great.
And don't forget to check the description for access to additional resources that can help you go even further. Okay, let's unpack this. We're starting at the very foundation, the physical network architecture.
Right.
Think of it as the concrete and steel of your digital city, and at its heart, tirelessly directing traffic, are switches.
That's right. Switches are absolutely foundational to modern networks, acting as intelligent traffic controllers. Back in the day, we used hubs, which were essentially digital party lines. Every message went to every device. It was incredibly inefficient.
Oh yeah, I remember those. Like shouting in a crowded room.
Exactly. Like a postal worker shouting every letter's content down a busy street. Switches changed all that. They learn precisely which device is on which port and direct traffic efficiently to its intended destination.
Much better.
This direct point-to-point communication dramatically reduces unnecessary traffic, minimizes collisions, and, most importantly, significantly boosts overall network performance and security.
So no more shouting letters down the street. It's a precision delivery service. But I imagine not all switches are created equal. There's a whole spectrum, from the simplest to the highly sophisticated, right?
Absolutely. At one end, you have unmanaged switches. These are your set-it-and-forget-it devices.
Plug and play.
Pretty much. They're plug and play, don't have an IP address for configuration, and require minimal fuss. Think of them for, like, a home office or a small business with just a few devices that just need to connect reliably. They simply do the essential job of switching packets.
Sounds great for simplicity. But what if you need more control, more oversight, more strategy?
Well, that's where managed switches come in. Precisely. Managed switches are the workhorses of enterprise environments. They offer extensive configuration options, accessible via a command line interface, often preferred by seasoned network admins for its power and precision.
It's the UI, yeah.
Or through a user-friendly web-based graphical interface, a GUI. Critically, they can be grouped for centralized management and are typically assigned an IP address, making them addressable and controllable from anywhere on the network.
Right.
This level of control is paramount for businesses needing to fine-tune traffic flow, enforce security policies, segment networks, and ensure optimal performance for mission-critical applications.
Now, traditionally, switches are layer 2 devices dealing with MS key addresses.
Correct.
But I've heard about switches that transcend this, operating at higher layers of the OSI model. How do they do that?
This is where it gets really interesting and shows how network devices are evolving. We have Layer 3 switches, which are a fascinating hybrid. They blend the high-speed forwarding capabilities of a traditional switch with the routing intelligence of a router. They support routing protocols and can make routing decisions based on IP addresses.
So they route.
They do. The key advantage is they're optimized for speed within a large local area network. For internal routing between large segments or VLANs in a data center, they can be significantly faster and often more cost-effective than dedicated routers.
Ah,
They're like a high-performance internal highway system for your data.
so a layer 3 switch is faster for internal routing. But then there's an even more advanced type, a layer 4 switch, which sounds like it's getting into the realm of understanding the content of the data itself.
Indeed. Layer 4 switches, often called content or application switches, are remarkably sophisticated. They interpret data from layer 4 all the way up to layer 7.
Wow, up to the application layer.
Yes. This allows them to perform incredibly advanced functions like intelligent filtering based on the specific content of an application request, gathering detailed statistics on application usage, and even advanced security functions such as load balancing based on the specific application being accessed or even the user's identity.
So really granular control.
Absolutely. Imagine directing web traffic not just to a server, but to the least busy server, specifically handling the shopping cart application to ensure a smooth user experience.
That's powerful.
This level of intelligence is a game changer for critical applications.
So whether you're a small business needing basic connectivity or a global enterprise demanding granular control, high performance, and advanced security, understanding this spectrum of switches from unmanaged to layer 4 is essential for building a network that scales with your needs.
Absolutely crucial. Now, moving from the raw functionality of switches to their security, it's vital to recognize a fundamental vulnerability, an open wall jack connected to a switch.
Yeah. Seems harmless enough.
It seems innocuous, but it's essentially an unlocked backdoor to your entire network. Someone could simply plug in an unauthorized laptop, gain immediate access, and potentially wreak havoc.
Yikes.
This is a surprisingly common, yet often overlooked, attack vector.
And there's a specific type of attack related to this vulnerability that really exploits a switch's intelligence, or rather, lack thereof under duress. The mass flooding attack.
Ah, yes.
Can you paint a picture of how that can cripple a network?
Oh, it's truly a nightmare scenario. A mass flooding attack works by an attacker rapidly sending a massive volume of frames, each with a different spoofed MS address, to a switch.
Okay.
The switch's MC address table, which stores the MSC addresses it has learned, and their corresponding ports, quickly becomes overwhelmed and overflows.
It just fills up.
Completely fills up. When this crucial table is full, the switch can no longer intelligently direct traffic. It's forced to revert to acting like an old-fashioned hub, broadcasting all incoming messages to all its ports. If an attacker is simply capturing traffic on one of these now broadcasting ports, they suddenly have access to every packet on that network segment.
Wow.
Confidentiality is completely gone, and your data is exposed.
That sounds devastating. So what's the countermeasure? You often talk about defense in depth, which seems incredibly relevant here.
Defense in depth is the absolute foundation. It's a layered approach to network security, acknowledging that no single solution is a silver bullet.
Right, layers.
You build multiple redundant layers of defense, so if one layer is breached or fails, others are still in place. It's about designing resilience into your security posture rather than relying on a single point of failure.
So let's get practical. How do we secure those switch ports against such threats? What are the immediate actions a network administrator should take?
Well, the first, most straightforward step is to disable any unused switch ports.
Simple enough.
If a port isn't connected to an authorized device, it shouldn't be active, period. It's a simple measure, but it immediately removes potential entry points. Secondly, and much more powerfully, implement port security.
Okay, what's that involve?
This feature on managed switches allows you to filter or limit the number of permitted MIC addresses on a specific port. For instance, you can configure a port to accept traffic only from a single specific MIC address associated with an authorized device, or perhaps limit it to just 2 if you have a phone and a computer sharing a port.
So you lock it down to known devices.
Exactly. These measures directly translate theoretical risk assessment into actionable, robust security strategy. They're your first line of digital defense.
Beyond securing individual ports, a critical aspect of physical networks is ensuring continuous operation, even if components fail. This means building in redundancy.
Essential.
But you cautioned earlier that redundancy can introduce its own set of problems, specifically network loops. How does the network prevent those?
That's precisely the challenge. While path redundancy is absolutely essential for fault tolerance, giving data multiple routes to travel, it can inadvertently create network loops.
Right.
Imagine if you have two switches and they're connected to each other by two different cables, creating a circular path.
Oh, cool.
Data packets could endlessly loop between them, consuming all available bandwidth, creating what we call a broadcast storm. This isn't just an inefficiency, it's a network meltdown, crippling all communication.
And that's where something truly elegant comes into play. The Standing Tree Protocol, or STP.
Yes.
This is like the sophisticated traffic cop for your network, actively preventing gridlock.
It's a brilliant solution. STP is a Layer 2 protocol specifically designed to prevent these switching loops and the resulting broadcast storms. It does this by intelligently identifying all redundant paths in a network and then strategically disabling certain ports to create a loop-free logical topology.
So the physical cables are still there, but only one path is active.
Exactly. So the physical connections are still there for redundancy, but STP ensures only one path is active at any given moment.
How does it achieve that intricate dance? It sounds quite complex to manage dynamically.
It's a marvel of network engineering, actually.
Oh.
STP operates through a series of steps. First, it elects a root bridge for the entire network, essentially the central authority for path decisions.
Okay, a boss switch.
Kinda, yeah. All other switches then calculate their least cost paths to this root bridge. Based on these calculations, each switch determines its the port closest to the root bridge and its designated ports for each network segment, which are responsible for forwarding traffic.
Right.
Any remaining ports that would create a loop are then put into a blocking state, effectively disabling them to break the loop.
Ah, clever.
If a primary path fails, STP quickly re-enables a previously blocked port to restore connectivity, ensuring continuous operation without manual intervention.
So it's constantly monitoring and adapting, like a self-healing network.
Exactly. Switches running STP communicate by sending special frames called Bridge Protocol Data Units, or BPDUs.
EPUs.
These BPDUs allow them to share information about their topology and quickly detect changes or failures. Many modern switches also include features like storm control to mitigate the impact of broadcast storms even before STP fully converges.
Good backup.
And for even faster convergence and more robust features, newer variations like RSTP, Rapid Spanning Tree Protocol, TreeLL, SPB, and RPVST+ have been developed. Understanding these loop prevention mechanisms is absolutely critical for anyone involved in network design and troubleshooting, as a stable network is a functioning business.
Managing a few switches might be straightforward, but what happens when an enterprise network scales to dozens or hundreds of switches, alongside routers, firewalls, and servers?
Yeah, it gets complex fast.
All needing fault tolerance, redundancy, and load balancing. That sounds like a recipe for chaos without a clear strategy.
That's where hierarchical network design becomes absolutely indispensable. It takes that overwhelming complexity and organizes it into logical, manageable layers,
Okay.
making the network easier to design, deploy, and troubleshoot. The most common and effective is the three-tier architecture.
And those three tiers, what do they represent in our network city analogy?
Good question. At the lowest level, you have the access or edge layer. This is where all your end devices, computers, phones, printers, IoT devices connect to the network.
Local streets.
Exactly. Think of it as the local streets that get you to every individual house or business. Above that is the distribution or aggregation layer, which aggregates traffic from multiple access layer switches. This layer is where network policies are enforced, routing between VLANs occurs, and quality of service, QoS, is managed.
Arterial roads.
You got it. The major arterial roads collecting traffic from many local streets and directing it towards the core. Finally, at the very top, you have the core layer, which is the high-speed backbone of the entire network. It's designed for fast, efficient transport of massive amounts of traffic between distribution layers.
The interstate highway system.
Precisely, prioritizing speed and capacity above all else.
That makes perfect sense for traffic flowing in and out of the data center, what we call north-south traffic.
Right. Client to server, mostly.
But with the rise of virtualization and cloud applications, a lot more traffic is moving between servers within the data center. That's east-west traffic. And I imagine traditional hierarchical design struggled with that.
You hit the nail on the head. In traditional hierarchical designs, east-west traffic often had to hairpin, meaning it would travel up to the distribution or even core layers, only to come back down to another server in the same data center.
Inefficient.
Very. It introduced unnecessary latency and inefficiency. This challenge, driven by the massive growth of server-to-server communication, led to a more modern approach specifically for data centers.
And that modern approach is the spine and leaf architecture, a design that has truly revolutionized data center networking.
Exactly. Spine and leaf fundamentally flattens the network, collapsing the traditional core and distribution layers into a highly interconnected spine layer. The leaf switches are typically top-of-rack POR switches, meaning servers and other devices within a single rack connect directly to a leaf switch.
Okay.
While historically you might have seen end-of-row EO switching, where multiple racks connect to switches at the end of a row, TOR is far more common today. The critical design principle is that every leaf switch connects to every spine switch, and vice versa, creating a highly interconnected, non-blocking fabric.
Every leaf connects to every spine.
Yeah.
Wow.
And the benefits of this flat, interconnected design are truly transformative for modern data centers. It offers dramatically improved redundancy because if one spine switch fails, traffic can instantly reroute through any of the others.
Nice.
This leads to significantly decreased latency for east-west traffic, as any leaf can reach any other leaf through a maximum of just 2 hops.
2 hops max, that's fast.
Which translates to increased performance, especially for microservices and distributed applications. It also provides improved scalability. You can add more spines or leaves without re-architecting the entire network.
Easier to grow.
Plus, increased security is inherent because traffic paths are more predictable and controllable, facilitating microsegmentation. And critically, it often results in reduced expense by simplifying the architecture and allowing for less expensive but highly capable data plane devices. This aligns perfectly with the insights from CSPI, emphasizing reducing data center complexity and accelerating automation, integration, and security, and moving away from legacy approaches.
These design principles are all about ensuring continuous operation. So let's talk about keeping everything running smoothly. Network availability and redundancy.
Non-negotiable.
They're not just nice-to-haves anymore. They're non-negotiable in today's always-on world. What exactly do we mean by availability in a network context?
Availability refers to the level of reliability by which a resource can be accessed by authorized personnel. It's essentially a measure of uptime, how often a service is operational.
Uptime percentage.
Exactly. High availability, AJ, then, refers to systems designed to function reliably and be available nearly all the time. Think of the 5 nines availability, 99.999% uptime.
5 nines.
Which translates to just over 5 minutes of downtime per year. For critical business systems, every second of downtime can mean lost revenue, damaged reputation, or compliance issues.
Yeah, huge impact.
You can even measure this directly. On Linux systems, the uptime command, and on Windows, it's visible in the task manager.
And closely related to availability is fault tolerance. Many people confuse them, but there's a subtle yet incredibly important difference for system design.
There is. Fault tolerance is the ability of a system to continue operating without interruption, despite the failure of one or more components. The distinction is between a failure and a fault. A fault is a defect or an undesirable state in a component, for example, a faulty power supply that's generating intermittent errors.
Okay, something's wrong, but it's still working, mostly.
Right. A failure is when that fault actually causes the system to stop functioning as intended, like the server completely shutting down because the power supply finally died.
Got it. Fault leads to failure.
Fault-tolerant systems are explicitly designed to detect a fault and immediately switch to a redundant component before that fault escalates into a failure that impacts users. It's about preventing an incident from becoming an outage.
So how do networks achieve this level of resilience? What are some of the key techniques architects employ to build such robust systems?
One excellent technique, often overlooked but incredibly powerful, is link aggregation.
Link aggregation.
This is also known as port aggregation on Cisco devices or NIC teaming on Windows servers. It involves combining multiple network interfaces or ports into one single logical interface.
So you're essentially bonding several physical connections together to act as one super connection. What are the practical advantages of doing that for a business?
Exactly. The primary advantages are significant. First, increased total throughput, allowing you to push more data across that combined link than any single cable could handle.
More bandwidth.
Second, and perhaps even more critical for resilience, is automatic failover. If one of the physical links in the aggregated group fails, the others immediately pick up the slack without any interruption to service.
Seamless failover.
Nice. And the third, it provides load balancing, intelligently distributing traffic across all the active links, ensuring optimal performance. Many manufacturers use LACP, Link Aggregation Control Protocol, for dynamic coordination between devices on these aggregated connections, ensuring they work together seamlessly and intelligently.
We also hear about load balancers and clustering in this context, extending this idea of resilience even further up the stack.
Indeed. Load balancers are dedicated devices or software that intelligently distribute incoming network traffic across multiple servers or other devices.
Spreading the work.
Exactly. This prevents any single server from becoming a bottleneck, ensuring optimal performance and efficient resource utilization, especially for web servers or application servers handling high volumes of requests. If you have several identical web servers, a load balancer makes sure traffic is spread evenly among them, optimizing response times and preventing overload.
And clustering.
Clustering, on the other hand, groups multiple devices together so they appear and function as a single, more powerful and resilient device. If one server in a cluster goes down, another takes over its role instantly, ensuring continuous service.
Like a team of servers acting as one.
Precisely. These concepts, availability, fault tolerance, link aggregation, load balancing, and clustering, are absolutely critical for ensuring business continuity and meeting stringent service-level agreements. They are fundamental tools for designing robust, troubleshootable networks that can withstand the inevitable faults of the physical world.
Here's where it gets truly transformative. We've been talking about the physical backbone, the concrete and steel.
Right, the hardware.
But what if I told you that some of the most powerful advancements in network architecture today aren't built on any physical hardware at all?
Going virtual.
This is where it gets revolutionary. Virtual architecture, at its core, is virtualization, the creation of a virtual or logical version of something physical. It's like having a digital doppelganger.
A digital twin, yeah.
This includes everything from virtual machines to virtual LANs. So instead of needing a separate physical computer for every single task or operating system, you can carve up one powerful machine into multiple virtual ones. It sounds incredibly efficient.
It is.
But what exactly does that entail? What are the key terms we need to understand this fundamental shift?
Exactly. It's about getting more from less, often dramatically more. The core terminology includes the host, which is the physical machine, the powerful server running the virtualization software,
The physical box.
the guest, which is the virtual instance itself, like a virtual machine, VM, running on that host, and the hypervisor, the crucial software layer that makes all of this possible.
The magic layer.
Pretty much. To elaborate on how VMs work, they essentially emulate a complete physical computer system. Each VM runs its own isolated guest OS, whether that's Windows Server, various distributions of Linux, or something else entirely.
Its own operating system.
Critically, each VM also gets its own virtual hardware. This includes virtual network adapters, virtual storage, and virtual memory. It's all managed and coordinated by the Virtual Machine Monitor, VMM, which is part of the hypervisor. The VMM ensures each VM operates independently, securely, and without interference from other VMs, while still efficiently sharing the underlying physical resources.
So they think they have their own hardware, but they're sharing.
It's like having multiple independent operating systems all believing they have exclusive access to a machine, yet all sharing one physical box.
And the advantages of this approach, as highlighted by sources like Scale Computing and ConnectWise, are truly compelling for businesses looking to optimize their IT.
Absolutely. Virtualization offers immense benefits. You get incredibly efficient resource use, consolidating many server workloads onto far fewer physical machines,
These are boxes.
leading to significant cost and energy savings, less hardware, less power, less cooling. It provides excellent fault and threat isolation. If one VM gets compromised or crashes, it typically doesn't take down the entire host or other VMs.
Self-contained failure.
And it greatly simplifies backups, recovery, and replication, often allowing for quick snapshots and restoration in minutes.
Big business impact there.
Huge. Think of the business impact. You can spin up new servers for testing or development in moments, scale resources for a new application without buying new hardware, or quickly recover from a disaster with minimal downtime. It's used for everything from server consolidation to creating isolated application development testing environments and providing platform-agnostic execution for software deployment. The hypervisor truly is the unsung hero, the backbone of this entire virtual machine architecture.
Right, the software making it possible.
It's the software layer that sits directly between the physical hardware and the virtual machines. Its job is to manage and allocate all the physical hardware resources: CPU cycles, memory, storage I/O, network bandwidth across multiple VMs. It's what ensures each VM operates independently and securely, maintaining that illusion of dedicated hardware while sharing the underlying physical server.
And there are different types of hypervisors, right? Some are more direct, while others operate on top of an existing operating system. What's the strategic implication of choosing one over the other?
Exactly. We categorize them into two main types, and the choice has significant performance and security implications. Type 1, or bare metal hypervisors, are installed directly on the physical hardware without an underlying operating system.
Straight onto the metal.
Yep. Examples include VMware ESXi, Microsoft Hyper-V, Citrix Hypervisor, and Scale Computing's S-Hypercore. Because they run directly on the hardware, they offer superior performance, robust security, and are the preferred choice in enterprise data centers where efficiency, reliability, and security are paramount. They eliminate the overhead of a host OS. Then there are Type 2, or hosted hypervisors, which run as an application on top of an existing operating system. VirtualBox and VMware Workstation are common examples.
Like running an app.
Exactly. These are ideal for less intensive tasks like testing, development, or running a different OS on your personal laptop, where the slight performance overhead of the host OS isn't a critical concern. Regardless of type, the hypervisor's dynamic resource management capabilities are key. They ensure fair distribution of CPU, memory, and I/O bandwidth, providing critical isolation and preventing any single VM from monopolizing resources and impacting others.
So if we look at the bigger picture of choosing between physical and virtual servers, as discussed by ConnectWise, the hypervisor plays a massive role in that strategic decision for businesses. Let's weigh those pros and cons.
Definitely worth comparing.
For physical servers, the pros still include higher raw performance and absolute isolation. You get dedicated resources, no sharing.
Total control.
This offers predictability and complete control over the hardware, making them ideal for truly resource-intensive applications, highly security-sensitive workloads that demand ultimate isolation, or legacy systems that simply can't be easily virtualized. However, the cons are significant. Higher implementation costs for hardware, physical space, power, and cooling.
The upfront costs, yeah.
Challenging scalability, as you have to buy, rack, and configure new hardware every time you need more capacity. And complex migration when moving applications from one physical server to another.
Right. Migrations can be painful.
Now, virtual servers completely flip many of those drawbacks on their head. Their pros are crystal clear. Incredible efficiency by maximizing hardware utilization, seamless scalability, you can easily scale VMs up or down in minutes.
Elasticity.
Significant cost effectiveness due to lower hardware and power consumption, much easier deployment, and rapid recovery thanks to snapshots and backups. This makes them ideal for dynamic business models, development agencies, and startups that need agility.
Big advantages for flexibility.
But even virtual servers aren't a silver bullet. They come with their own set of considerations.
Indeed. Potential performance degradation can occur due to shared resources if the host isn't properly provisioned or managed.
The noisy neighbor problem.
Sometimes, yeah. And while modern virtualization technologies are highly secure, there are specific cybersecurity concerns related to the hypervisor itself or potential VM escape vulnerabilities, which require specialized security tools and practices. What's truly fascinating here, and what many organizations are finding optimal, is a hybrid approach.
The best of both worlds.
Often, yes. Combining both physical and virtual servers allows them to leverage the specific benefits of each, optimizing performance, cost, and resilience across their diverse workloads. It's about strategically placing the right workload on the right infrastructure, which is a core part of designing robust and flexible logical and physical networks.
Moving into the virtual realm of machines means we also need to rethink how these virtual machines connect to the network.
Right, virtual networking.
Just like a physical computer, every VM needs a network interface, which in this case is a VNIC, or Virtual Network Interface Card. Upon creation, each VNIC is assigned a brand new MSC address.
And just as physical machines connect to physical switches, virtual machines connect via virtual switches, sometimes called virtual bridges.
Software switches.
Exactly. These are entirely software-based, controlled by the hypervisor, and allow VMs on a single host to communicate with each other, and crucially, to pass traffic across the physical network. You can even have multiple virtual switches configured on one host, providing sophisticated internal network segmentation.
Okay, so the VNIC connects to a virtual switch. How does that virtual switch actually connect the VM to the outside world or isolate it? What are the practical implications of the different connection modes for business?
The connection modes. Very important. There are three common and crucial modes for how a VM connects to the network. In bridged mode, the VNIC acts as if it's directly connected to the physical network, bypassing the host's IP stack.
Like it's plugged right into the physical switch.
Essentially, yes. It accesses the physical network directly using the host's physical NIC as a conduit, and the VM obtains its own IP address, default gateway, and subnet mask from the network, just like any other physical device. From the perspective of other network nodes, the VM appears as another full-fledged client or server, completely unaware it's virtual.
So it gets its own IP on the main network.
Correct. This mode is ideal for servers that need to be directly accessible on the network at a specific IP address, like mail servers, web servers, or domain controllers.
So bridged mode makes the VM a full participant on the physical network. What about NAT mode? How does that change the dynamic?
In NAT mode, the VNIC relies on the host machine to act as a network address translation NAT device.
NAT, like my home router.
Similar principle. The VM gets its IP addressing information from its host, typically a private IP address within a virtual network created by the hypervisor. The host then translates the VM's private IP address to its own public IP address when communicating with the external network.
So the VM hides behind the host's IP.
Exactly. This is incredibly useful for VMs that need outbound internet access but don't need to be directly accessible from the outside, like a client workstation for web browsing or a development environment. It effectively places the VM behind the host, providing a layer of protection.
And finally, there's host-only mode. When would you use that, given its isolated nature?
Host-only mode completely isolates the VM from the external physical network. The VM can only communicate with the host machine and other VMs running on that same host, but no one else.
Totally cut off.
Right. It's perfect for creating isolated testing environments, like a sandbox lab where you want to experiment with potentially risky software, develop malware analysis tools, or build a closed network for training, all without affecting your production network or the internet.
Makes sense for secure testing.
Understanding these different modes is absolutely crucial for effectively designing, configuring, and securing virtualized environments. It's about choosing the right tool for the right job, ensuring both connectivity and necessary isolation.
Now, what's truly fascinating is that we're not just virtualizing entire machines. We're seeing a revolutionary shift where specific network devices and functions themselves are being virtualized.
Yeah, NFV.
Moving beyond dedicated physical boxes. This is where network functions virtualization, or NFV, comes in.
Yeah.
Imagine taking a physical firewall or a router and running it as software on an inexpensive generic server. What are the big wins for businesses here?
The advantages of NFV are profound, driving immense business agility. Virtual devices can be quickly and sometimes automatically migrated from one server to another if there's a hardware failure, or during maintenance, minimizing downtime.
Much more flexible.
Resources are utilized far more efficiently because you can dynamically scale up or down the virtual network function as needed, eliminating the need to over-provision hardware.
Scale on demand.
And services can be easily scaled to meet changing network demands without the time and expense of provisioning new physical hardware. Imagine being able to spin up a new, fully configured firewall for a new branch office globally in minutes, without a single physical box being shipped.
Wow, that changes everything.
It fundamentally changes the speed at which an enterprise can innovate and adapt. However, it's not without its considerations. Licensing can be complex, there can be potential latency challenges compared to dedicated hardware.
Performance trade-offs.
Sometimes. And some organizations still harbor a lack of confidence in virtual firewalls compared to their physical counterparts for critical high-performance security functions.
Building on NFV, we have software-defined networking, or SDN. This takes network management to an even higher level of abstraction and centralized control. It sounds like a philosophical shift in how we think about networks.
It absolutely is a philosophical shift. What's fascinating here is that SDN is a centralized method of managing the network and its devices by fundamentally decoupling the path and filtering decisions from the physical or virtual devices that actually carry the network traffic.
Separating the brain from the brawn.
That's a great way to put it. In traditional networks, each router and switch makes its own decisions. With SDN, you separate the brain from the limbs.
So the individual network devices just do what they're told, like dumb pipes. And a central brain makes all the routing and forwarding decisions.
Exactly. SDN divides the functionality of network devices into distinct planes or layers. The data plane, or infrastructure plane, consists of the physical or virtual devices, the actual switches, routers, and firewalls that physically send and receive traffic.
The limbs.
The control plane is the intelligent decision maker, embodied by the SDN controller, which determines the best paths for network traffic and pushes those instructions down to the data plane devices.
The brain.
Then you have the application plane, which facilitates communication between the control plane and various network services and applications. And finally, the management plane, which handles remote management protocols for monitoring, configuration, and analysis.
Okay. Different layers of control.
Communication between the SDN controller, the brain, and the network devices, the limbs, happens via a southbound interface.
Controller to devices.
And communication between the SDN controller and various applications happens via a northbound interface, typically using APIs.
Controller to apps.
While SDN introduces initial complexity and a learning curve, its benefits are immense for large enterprises with thousands of devices. It significantly increases operational efficiency, reduces costs by allowing less expensive data plane devices, and enables far more agile and programmable network management. Juniper's vision, as outlined in their insights, talks about automation frameworks infused with telemetry, analytics, and machine learning for a predictive and adaptive autonomous network.
Self-healing networks.
Essentially, systems that can self-discover, self-monitor, self-configure, and even self-heal. This truly streamlines complex network management and supports agile IT service provisioning, which is absolutely essential for today's cloud-centric, microservices-based applications.
Now we arrive at the expansive landscape of cloud architecture. This isn't just a trend, it's a fundamental paradigm shift in how IT resources are delivered, consumed, and even thought about.
It really is a different way of doing things.
At its core, cloud computing has a few defining characteristics that set it apart.
Yes, these fundamental characteristics include on-demand self-service, meaning you can provision computing resources like servers, storage, or databases as needed without human intervention and often in minutes.
Click and deploy.
Then there's broad network access, making these services available over the network from anywhere on any device. Critical is resource pooling, where computing resources are pooled to serve multiple consumers. This is also known as multi-tenancy.
Shared resources.
Where resources are shared but isolated. Then we have rapid elasticity, allowing resources to be scaled up or down quickly and flexibly to meet fluctuating demands, which we also call elasticity.
It's a sailing easy.
And finally, measured service, where resource usage is rigorously monitored and billed, so you only pay for what you consume, a true utility model.
Pay for use.
Exactly.
And a relatively newer but increasingly important concept within the cloud is cloud native. This isn't just running things in the cloud, it's building them for the cloud.
Exactly. Cloud native refers to a design approach that specifically leverages the unique advantages and capabilities of cloud computing from the ground up. This often includes using highly dynamic compute services like serverless functions, where you run code without having to manage a server yourself.
Serverless cool.
Or infinitely scalable storage services that can hold massive amounts of data in various formats. It's about building applications that are inherently flexible, resilient, and scalable within a cloud environment, rather than simply porting traditional applications.
The benefits of this approach are truly transformative for businesses, as highlighted by CloudDefense.ai and MoldStud. It sounds like a complete strategic advantage.
Oh, absolutely.
We're talking about vastly simplified IT infrastructure management because the cloud provider handles much of the underlying complexity like hardware maintenance, security patching, and even server provisioning.
A less operational burden.
This offers unparalleled scalability, allowing organizations to grow from a small startup to a global enterprise without massive upfront investments in physical infrastructure. It's incredibly cost-effective, shifting from large, depreciating capital expenditures, CapEx, to flexible, pay-as-you-go operational expenditures.
OpEx. OpEx versus CapEx, a huge
And
shift.
the extreme flexibility enables access from anywhere, supporting remote work and global operations seamlessly. And for businesses, disaster recovery is significantly enhanced,
Much easier in the cloud.
with cloud vendors offering robust backup and recovery protocols that would be prohibitively expensive to build in-house.
What's truly fascinating here is the comprehensive nature of these benefits. Cloud computing also provides comprehensive security and compliance measures, often exceeding what individual businesses can achieve on their own, especially for smaller enterprises.
Access to top-tier security.
It powerfully enhances DevOps by providing developers with immediate access to the infrastructure needed for faster application delivery and continuous integration. Plus, the simple accessibility of data and resources from virtually anywhere makes it a true game changer for collaboration and business agility. MoldStud even points out that by 2025, a staggering 85% of businesses are expected to adopt virtualization-driven services,
Wow, 85%.
underscoring this massive irreversible shift. To truly understand how cloud computing is delivered, we categorize services into different models. Think of it as a spectrum of shared responsibility, who manages what,
Okay, the service models.
from the hardware up to the application itself. At one end, you have traditional on-premises, where you, the organization, manage absolutely everything. Applications, data, runtime, middleware, operating system, virtualization, servers, storage, and networking.
We own it all.
It's all in-house, all your responsibility, like owning and maintaining your entire farm.
So a completely do-it-yourself approach with all the control, but also all the burden. Then we move into the cloud models, where some of that responsibility shifts to the provider.
The first cloud model is IaaS, or Infrastructure as a Service. Here, the cloud provider gives you the fundamental virtualized computing resources, virtual machines, raw storage, and virtual networks over the internet.
The basic building blocks.
Right. You, the customer, manage the operating system, applications, and data, but the provider handles the underlying of virtualization, physical servers, storage, and networking. This is like renting the land and building materials for your farm. You still build the barn and plant the crops, but you don't own the land itself.
Still need hardware knowledge.
It requires you to have a decent understanding of hardware infrastructure, but frees you from owning the physical hardware.
So a little less responsibility than on-premises, but still a lot of control over your software stack. Next up is PaaS, Platform as a Service. What does that abstract away?
With PaaS, the cloud provides a complete platform for developing, running, and managing applications. The provider handles everything from the runtime environment, middleware, operating system, virtualization, physical servers, storage, and networking.
So you just handle the code and data.
Primarily, yes. Your responsibility is primarily your application code and data. This is like renting a pre-built barn with all the necessary tools and soil. You just bring your seeds and start planting. It allows developers to focus entirely on coding and innovation without worrying about any underlying infrastructure management.
And then the most hands-off approach for the end user, SaaS, Software as a Service. This is what most people interact with daily without even realizing it.
That's right. SaaS is where the cloud provides ready-to-use software applications over the internet. Think Office 365, Salesforce, or even your favorite streaming service.
Just use the software.
As an end user, you simply access the application via a web browser or a client, and the cloud provider manages everything else, the entire stack, from the application down to the networking. It requires minimal setup and management from the user. This is like simply buying produce from the grocery store. All the farming and processing is handled for you.
Simple.
And if we connect this to the bigger picture, there's also AaaS, or anything as a service, which is a broader model where the cloud can provide any combination of functions based on client needs, reflecting the immense flexibility of cloud offerings. Choosing the right model depends entirely on your desired level of control, cost considerations, and management burden, directly influencing your network design and component selection.
Just as there are different service models for how cloud services are delivered, there are also different deployment models for where these cloud environments physically reside and how they're accessed.
Right, where the cloud lives.
The most common and widely used is the public cloud. These services are offered over the public internet by third-party providers like AWS, Azure, or Google Cloud.
The big players.
They're typically pay-as-you-go, scalable, and shared among many users or tenants. Think of it like a massive apartment building. You get your own unit, but you're sharing the building's underlying infrastructure with many others. It's cost-effective and flexible.
Then you have the private cloud. This is a cloud environment that is dedicated to a single organization.
Just for you.
It can be physically located on premises in your own data center, giving you complete control over the hardware, or it can be hosted by a third-party provider, but it's still exclusive to your organization, offering greater control, privacy, and tailored security. This is like owning your own detached house, dedicated resources, complete control, but also all the responsibility.
And sometimes organizations with similar needs or concerns might share a cloud, right? Like a gated community.
That's a good analogy for a community cloud. It's shared by several organizations with a common concerns, perhaps specific security requirements, compliance standards, or unique mission objectives. It's a niche but highly effective model for collaborative groups or industry-specific consortia.
Most businesses today aren't choosing just one model. They're increasingly talking about hybrid cloud.
Very common now.
A hybrid cloud is a sophisticated combination of public and private clouds, allowing data and applications to move seamlessly between them.
Connecting the two.
This offers incredible flexibility, enabling organizations to keep sensitive data in a private cloud for enhanced security or compliance, while leveraging the immense scalability and cost-effectiveness of a public cloud for less sensitive or burstable workloads. So you mix and match.
It's like having your house, but also renting an apartment downtown for burst capacity or specific workloads. You get the best of both worlds, moving things around as needed.
And then there's multi-cloud, which takes it a step further.
Multi-cloud refers to using multiple public cloud providers simultaneously, rather than being locked into a single vendor.
Using AWS and Azure, for example.
Exactly. This significantly enhances resilience, allows you to leverage best-of-breed services from different providers for specific tasks, and is a powerful strategy to prevent vendor lock-in. These deployment models offer organizations a diverse set of strategic options to balance cost, control, security, and scalability, allowing them to optimize their digital infrastructure for specific business needs. When it comes to truly mastering hybrid cloud architecture, as IBM details, it's about far more than just connecting an on-premises data center to a public cloud.
More involved than just a VPN connection.
Much more. It's about seamlessly bringing together multiple disparate environments, public cloud, private cloud SAROs, on-premises infrastructure, and even edge computing environments as a single, unified, and intelligently managed IT infrastructure. The goal is to maximize the potential of IaaS, PaaS, and SaaS, all with the flexibility for a multi-cloud approach, and, critically, avoiding vendor lock-in.
And the fundamental elements of this modern hybrid cloud architecture have evolved significantly. It's no longer just about traditional service-oriented architecture.
What's truly revolutionary here is the shift towards microservices-based architecture. Imagine a traditional application as a giant, intricately woven tapestry. If one thread breaks, the whole thing can unravel.
Monolithic apps.
Right. Microservices is like breaking that tapestry into hundreds of smaller, independent patches. Each patch is a service, developed, deployed, and managed independently.
Small, independent pieces.
These are then packaged into lightweight, portable executables called containers. Docker's emergence in 2013 provided a universal packaging structure for these containers.
SOC containers, yeah.
And Kubernetes automates their deployment and management across these hybrid cloud environments. This containerization paradigm allows for unprecedented portability and isolation, meaning workloads can easily shift between private, public, or on-premises environments, scaling up and down as needed without ever needing to restart the entire application.
That incredible flexibility fundamentally changes how businesses approach their cloud strategy. It's less about rigid hosting decisions and more about dynamic workload placement.
Exactly.
So for organizations looking to build or optimize such an architecture, what are the absolute key design considerations?
Okay, first, a robust modernization strategy is vital. You can lift and shift entire applications to the cloud quickly, though it might not fully optimize cloud benefits.
Quick, but maybe not optimal.
A more nuanced approach is to refactor, modifying parts of an application to be cloud-ready, often adding APIs for better integration, which is a phased, iterative approach.
Modify it for the cloud.
The most sophisticated but expensive is to re-architect, a complete rewrite into modular microservices, maximizing cloud benefits and return on investment. This is a business decision, not just a technical one.
Biggest effort, biggest reward, potentially.
Second, a unified control plane is essential. This centralizes management for consistent operations across all environments, abstracting away the complexities of individual cloud service providers.
A single dashboard.
Sort of, yeah. Your single pane of glass, allowing for dynamic workload placement, consistent compliance management, and building highly available Paris capabilities across your entire hybrid estate.
And then there are specific architectural patterns that act as digital traffic cops and security guards within this complex hybrid environment,
Yeah.
like API gateways and service meshes.
Yes, these are critical for managing communication. An API gateway acts as a unified front door, handling north-south traffic interactions coming into or leaving your hybrid cloud.
Traffic in and out.
It manages user authentication, rate limiting, traffic management, and crucial security guardrails. It's your network's bouncer and concierge. A service mesh like Istio handles east-west traffic, the secure service-to-service communication within a cluster.
Traffic between services.
It provides intelligent load balancing, sophisticated routing rules, telemetry for deep monitoring, and distributed traceability, often working invisibly as a sidecar to your containers, ensuring every microservice can talk securely and efficiently.
Fifth, security in a hybrid cloud requires a meticulously designed, multi-tiered approach.
Security everywhere.
This means securing perimeters with cloud service provider tools and API gateways, enforcing granular control policies with the service mesh and orchestration platforms, implementing micro-segmentation to define granular access control policies for each individual service, and of course, robust encryption for all data at rest and in transit.
It's about building security into the architecture, not bolting it on.
And just, network connectivity needs careful consideration.
How you connect everything.
You have options like public IP addresses over the internet, most accessible but higher latency, VPNs, more predictable latency, higher security through encryption,
VPNs are common.
or dedicated interconnects through common points of presence, least latency, maximum security, but typically the most expensive. The choice here dramatically impacts performance, reliability, and cost, and must align with your business's needs.
And finally, a bias towards open source and development platforms and underlying technologies is crucial for true hybrid cloud flexibility. Why is that?
Avoid vendor lock-in.
Absolutely. Open source architectures like Linux, Kubernetes, containers, and Red Hat OpenShift are vital. They enable portability, explicitly prevent vendor lock-in, and provide rich features backed by a vast, vibrant community. This allows developers and operations teams to manage their infrastructure regardless of the underlying technology or cloud service provider, giving businesses ultimate flexibility and control. This comprehensive approach enables organizations to achieve high performance, resource efficiency, cost savings, and resilience, providing a robust framework for developing any professional network proposal to address a business problem.
Once you've strategically chosen your cloud models and deployment strategies, you still need to interact with and manage these cloud resources. You have several powerful options for connecting to and managing your cloud environment.
Ways to talk to the cloud.
The most common ways are through a graphical user interface, GUI, which is typically a web-based interface offering easy visual management for everyday tasks.
Clicky, clicky.
A command line interface, CLI, preferred by many developers and administrators for its speed, precision, and especially for scripting and automation.
The power user way.
An SDK, software development kit, for building custom applications that programmatically interact with cloud services, and APIs, application programming interfaces, which allow direct programmatic interaction with cloud services, forming the backbone of all automated cloud operations.
APIs are key for automation.
Within the cloud, services are generally categorized by their purpose, making it easier to navigate the vast offerings.
Yeah, they group them logically.
The most popular categories include compute services for virtual machines, containers, and serverless functions, networking services for virtual private clouds, load balancing, DNS, and content delivery networks.
Storage services for block storage, object storage, and various database solutions, and security services for identity and access management, encryption, key management, and threat detection.
Lots of options.
A huge menu.
And when you're relying on a cloud provider, understanding SLAs or service-level agreements is paramount. What should businesses be looking for in those agreements, especially regarding key metrics for cloud-hosted resources?
Indeed. These SLAs are your contract with the cloud provider, defining the guaranteed performance, availability, and expectations of your services. Key terms to look for and understand are availability, how often the service is operational and accessible; durability, the likelihood that your data will be preserved without loss;
How safe is my data?
reliability, the consistency of performance over time; and resiliency, the ability of the system to recover gracefully from failures.
How quickly does it bounce back?
These are vital for business continuity, disaster recovery planning, and ensuring your cloud strategy meets your operational needs and legal obligations. Don't just skim them. Truly understand what your provider is guaranteeing.
So we talked about all these amazing cloud services and virtual architectures. But there's a flip side, right? Managing all these dynamic virtual resources can introduce entirely new challenges,
Like keeping track of it all.
like accruing unintended charges or losing track of changes in your rapidly adapting infrastructure. This is where automation and orchestration become absolutely critical. They're no longer a luxury, but a necessity.
What's fascinating here is that modern infrastructure is in constant flux. This concept of a dynamic inventory infrastructure that's always changing based on demand, new deployments, or scaling events makes manual management utterly impossible.
Too much to track manually.
Software developers rely on well-defined pipelines to support the various phases of development, from initial coding to service interactions and data progression. These pipelines define clear entry points, automated and manual transitions, and exit points for every task.
And a simple fundamental step towards bringing discipline and efficiency to IT operations is scripting.
Oh, absolutely.
You could write command line interface or CLI commands into scripts so you don't have to remember every single detail each time you execute a repetitive task.
Saves time, reduces errors.
This isn't just about saving keystrokes. It dramatically boosts efficiency, reduces human error, and ensures consistency across operations. So when we define these terms, automation is essentially a programmed, computer-generated response to an event. If X happens, then do Y.
Simple cause and effect.
But orchestration takes it a crucial step further, coordinating multiple automated tasks.
Precisely. Orchestration is the automation of many tasks that work together in a specific sequence, often defined in a template or playbook.
Like a recipe.
Think of automation as playing a single instrument perfectly, while orchestration is conducting an entire symphony, ensuring all the different instruments, automated tasks, play in harmony at the right time to achieve a complex outcome.
Conducting the automation orchestra.
Exactly. The benefits of both are immense for increasing efficiency, effectiveness, and security in network and cloud deployments. You get greater responsiveness to changes, tighter control over your environment, significant cost reduction. Enhanced security, improved repeatability of tasks, ensuring consistency every time, and dramatically fewer operational errors. Moldstud reports a staggering 30% reduction in manual operational tasks through prioritizing automation.
30%, that's huge.
This translates directly to more reliable services and more productive IT teams. If we connect this to the bigger picture, infrastructure as code, or IAC, as defined by Wikipedia, is a revolutionary process of managing and provisioning computer data center resources through machine-readable definition files.
Code files.
Essentially, using code rather than manual configuration or interactive tools.
So instead of a network engineer manually clicking through a GUI or physically connecting cables, they write a script or declarative file that describes their desired infrastructure.
Describe the end state.
And the system automatically builds and configures it for them. That's a powerful shift.
It's precisely that. IAC grew as a direct response to the scaling difficulties of utility computing and second-generation web frameworks, especially after the launch of AWS Elastic Compute Cloud and Ruby on Rails in 2006. Organizations quickly realized they needed to treat infrastructure like any other software project.
Infrastructure is software now.
Applying best practices like version control, testing, and automated deployment to rapidly provision and manage their applications and underlying networks. It blurred the lines between development and operations.
DevOps enablement.
Absolutely. And the advantages are truly compelling, impacting cost, speed, and risk, as noted by Moldstud and Wikipedia. It sounds like a game changer for IT teams. Financially, IAC leads to substantial cost reduction by eliminating manual effort and dramatically reducing human error, allowing teams to refocus on higher-value, innovative tasks.
More strategic work.
It dramatically increases speed by automating execution, allowing infrastructure to be spun up or reconfigured in minutes, and providing visibility across teams, making operations incredibly efficient.
Faster deployments.
Crucially, it profoundly reduces risk by eliminating human error from manual misconfigurations, which in turn decreases downtime and increases reliability. These attributes are absolutely foundational to enabling a DevOps culture, fostering collaboration, continuous integration, and continuous automation between development and operations teams.
There are also different ways to approach IAC, defining what you want versus how to get it, and different methods for deployment.
That's the distinction between declarative, functional, and imperative procedural approaches. Declarative IAC focuses on what the target configuration should be. You describe the desired end state, and the system figures out how to get there.
Tell it the goal.
Terraform, for example, is primarily declarative. Imperative IAC, on the other hand, focuses on how the infrastructure is changed. You define specific commands to be executed in a precise order, much like a traditional script.
Tell it the steps.
For sending these configurations to servers, there are two primary methods. The push method involves the controlling system directly sending instructions to the target server.
Push it out.
The pull method has the server retrieve its own instructions and configurations from the controlling system, ensuring it's always in its desired state.
Server pulls it in.
Exactly.
And the tools for IAC are becoming ubiquitous. For anyone looking to build a career in cloud computing or IT, I imagine proficiency in these is becoming a top skill.
Absolutely. Any framework that configures infrastructure programmatically can be considered IAC. We're talking about a vast ecosystem of continuous configuration automation, CCA tools.
BCIS tools.
Which are extensions of IAC, offering visibility, efficiency, and enterprise-level security. Notable examples include CF Engine, Puppet, Chef, SaltStack, Ansible, Terraform, Pulumi, and OpenTofu. AWS CloudFormation is another key tool for managing infrastructure within the Amazon cloud.
Lots of tools to learn.
On the security front, this shift also introduces new considerations. A 2020 cloud threat report from Unit 42, Palo Alto Networks, identified around 200,000 potential vulnerabilities in infrastructure as code templates.
Whoa, vulnerabilities in the code itself.
Highlighting that even code-driven infrastructure needs rigorous security auditing and careful design. It's about understanding that while IAC automates, the code itself still needs to be secure and conform to your risk assessment and security strategy.
Code security is critical.
For anyone looking to differentiate themselves in the cloud computing field, proficiency in IAC tools like Terraform or CloudFormation isn't just a plus. It's rapidly becoming a fundamental skill for career growth.
What's truly revolutionary here is how we're increasingly blending network and security operations with AI ops, artificial intelligence for IT operations.
AI for ops.
For years, traditional data center fabrics often lack comprehensive real-time telemetry. Network operations teams were flying blind, forced to rely on probes, agents, or sample traffic.
Guessing, real.
To try and piece together what was happening. This created critical telemetry blind spots and made true automation incredibly difficult.
You've highlighted a critical historical pain point. But with modern distributed services architectures, we now have accurate, ubiquitous telemetry natively across the entire data center fabric.
Built-in visibility.
This eliminates the need for external probes or agents, and even complex TEP aggregation networks, providing a true high-fidelity source of truth for all data center activity. It's like turning on every light in a dark room.
And this goes far beyond just collecting more data, right?
Right.
What other powerful capabilities does this unlock for network and security teams?
It absolutely goes beyond. Next-generation architectures provide things like MTTI, mean time to innocence, which is the ability to look back at traffic on a per-application basis to determine the precise root cause of poor performance. This is like having a network time machine that shows you exactly what happened and why.
Find the root cause faster.
This high-fidelity telemetry also enables robust integration via REST APIs with a wide variety of existing security and network performance tools, including Advanced Security ML, XDR, Application Dependency Mapping, ADM, AIOps platforms, SEMSOL systems, firewall compliance engines, and identity group mapping tools.
Connects to everything.
This rich, real-time data also empowers automated anomaly detection. The system can group related incidents, intelligently notify operations consoles and ticketing systems, and even trigger automation systems with real-time streaming data analysis.
Spots problems automatically.
This frees up operational teams from having to manually visualize and interpret raw telemetry, allowing them to focus on strategic responses rather than sifting through logs. By fully leveraging AI and machine learning tools with this complete high-fidelity telemetry from a fourth-generation data center fabric, we can automate security and network operations in ways that were previously impossible, creating truly self-managing and self-healing networks.
As infrastructure becomes more reliant on code, as we've just discussed with IOA, the need for tracking changes to that code becomes paramount.
Gotta track the changes.
This is where source control, or version control, comes into play, borrowing practices traditionally designed for software development and applying them directly to infrastructure management. Think of it like a meticulous historian for your network code. The core concept involves a central repository, which is a storage space for authoritative versions of your code.
The single source of truth.
When a new copy is made for development and testing, or for a specific feature, a branch is created. This allows multiple teams or individuals to work on different aspects of the infrastructure without interfering with the live production environment.
Working in parallel safely.
And as developers or network engineers write changes to the code, perhaps configuring a new virtual network or firewall rule, they commit those changes,
Save the changes with a message.
essentially uploading them to their working branch with a clear description of what was changed. This creates a detailed auditable history. If something goes wrong in the production environment, which is the live environment accessed by users, you can easily pinpoint the exact change that caused the issue.
Find the breaking chain.
And, critically, revert to a previous stable version of your infrastructure code.
Rollback capability. Essential.
Exactly. Tools like Git or GitHub are the version control software used to manage these various branches of code, often run concurrently by multiple developers or development teams.
Git is everywhere.
It's about accountability, collaboration, and the ability to roll back changes instantly, bringing software development best practices directly to infrastructure management, which is absolutely essential for managing modern dynamic networks. So we've journeyed from the tangible world of physical switches that direct our network traffic through the flexible realm of virtualization that lets us do more with less,
Lots of ground covered.
into the expansive landscape of cloud architecture that delivers IT as a service, and finally, embrace the groundbreaking efficiency of network automation and infrastructure as code. We've seen how modern network architecture isn't just about connecting devices. It's about strategic design, robust security, unparalleled scalability, and agile management,
It's a whole new ballgame.
all powered by a sophisticated blend of hardware, software, and intelligent automation. These elements are not just technical terms. They are the foundation for designing logical and physical networks, configuring security, and managing the intricate web of modern data communications.
Remember that silent revolution we talked about at the beginning?
I do.
It's precisely these profound shifts from static, manually configured infrastructure to dynamic, code-driven, cloud-native environments that are defining the future of business and creating incredible, future-proof career opportunities for those who truly understand these fundamentals.
Understanding is key.
The invisible forces are indeed reshaping everything, and now you have a deeper, more strategic understanding of them.
Thank you for diving deep with us today. Your curiosity is your greatest asset in this rapidly evolving world. If this deep dive sparked some aha moments or gave you a clearer roadmap for your career, please like, subscribe, and share the deep dive.
Please do.
It helps us bring more valuable insights like these directly to you. And as always, find additional resources in the description below.
As you look at the digital world around you, consider this. How might a deeper understanding of network architecture from the physical layer to the automated cloud change the way you approach problem solving in your own career or business? How can you leverage these architectural shifts to drive innovation and create resilient systems, not just for today, but for the future? Remember, strong connections aren't just technical, they're strategic. Until next time, keep your packets clean and your networks resilient.